So before we start, I just want to cover the usual the support channels at ilifu, and some useful resources. So primary point of contact for support-related issues is our support email. So that's support@ilifu.ac.za. You can find our user documentation at docs.ilifu.ac.za. So the documentation, I'm just going to quickly show for everyone's information. It's broken down into a getting started guide, which is basically a step-by-step guide for running through the ilifu services. And then there are more advanced topics under technical documentation, which expand on the initial guide, but there's also domain-specific information here. And today we have a new section, which is resource allocation guide, which we'll be covering during the session. In terms of the other support channels, we also have the ilifu status page, which is at status.ilifu.ac.za. And this is just shows the status of the cluster. There's a summary at the top of the page, and then the different components. So this is a really good place to first check if you're experiencing an issue, because it might be a general system issue. But if it's not listed here, please do contact us at support@ilifu, and we can follow up. And then finally, the training videos. So just for everyone's information, this has actually changed this week. The domain for it is now ilifu.ac.za/training, and that is where we will upload and the presentations, the recording and actual slides to our website, so you can come and view them here. And just for information's sake, the previous session in March is already available here as a resource, as are the previous training sessions from previous years. So you're welcome to use that. Obviously, the most up-to-date ones give the best information about the current services on ilifu. So getting back to slides, the topics for today, Robin will be covering parallelism on the cluster, and then Jordan will present on a topic that we haven't covered in detail before. This is important, and how to determine your resource requirements when submitting jobs or using services such as Jupyter. So I'm now going to hand over to Robin.
Okay, so before we get into the nitty-gritty stuff, let's just first establish some common terminology and concepts. So when we talk about a program, it's simply a set of instructions that a computer is going to execute sequentially, right? So if we look at this, a really simple program for calculating the average grade of a class, each line will get executed one after the other. And the loop, line 2 that you see here that tallies all the grades, needs to iterate through the entire list of grades one by one before the average can be calculated. So when we talk about parallelism, we want to be able to execute portions of a program simultaneously, which becomes possible when we have a bunch of CPUs at our disposal. So not only is the structure of the hardware important, the software also needs to be written in a way that lets it effectively utilize the hardware in parallel, which requires some kind of overall control mechanism. And as I've mentioned in previous sessions, the ilifu cluster is a group of connected nodes, each with its own RAM and multiple CPUs. So when you submit a parallel job to the cluster, you're essentially partitioning the job into smaller jobs that are going to run simultaneously. And the main advantage here is that you are speeding up the processing. So back to the really simple example, one could parallelize this program by splitting the class grades into 2 partitions. So you've got 2 lists of grades, for which we use the same program to get two averages, and then we combine the results by taking the average of the 2 partitions. That's a really basic example of how you could partition your data set and then process the data sets simultaneously, and then combine the result. So getting a bit more technical about how you should go about implementing a parallel job, we need to make the distinction between intra-node communication and inter-node communication. So intra-node being within a node, so between CPUs, and inter-node communication would be communication between separate nodes. So work can be distributed over many CPUs within a node, for which software called OpenMP is typically used. You can take advantage of using multiple CPUs with a variety of softwares, though. For example, Python's multiprocessing library, which actually comes standard with Python. And then work can also be distributed over multiple nodes as well, where portions of a node can be allocated as tasks for parallel processing. So OpenMPI is typically used for this, which requires a message passing interface wrapper, which I know sounds complicated, but I'll give some examples of this in a few slides. Sorry. So when considering parallelism on ilifu, the three things that we need to look at are the number of CPUs, the number of tasks, and the number of nodes a job will use. So a normal job is typically entirely serial and uses just one CPU, one task, and one node. If you want to use multiple CPUs, you can specify more than one CPU per task while keeping the nodes and the tasks at one. Then if you want to use more than one node or more than one task, you would change the variables nodes or tasks per node to be more than one. So I'll go into a bit more detail about why you need to take care when using more than one node when we look at some SBatch examples. And then also it's important to note that in general, you can't exceed 32 CPUs per node or tasks per node, because that's generally how many CPUs most of the nodes have. So looking at the SBatch syntax for these three variables that I've spoken about, you can see for a serial job that these simply stay at one, which I think is actually the default. So it's important to note here that if your job itself isn't properly coded to be parallel, so it doesn't use OpenMP or MPI, giving it more resources isn't going to have any effect on its processing time. And in fact, it will actually give your job a lower priority, meaning it might take longer to get a resource allocation. So that's why it's important to understand your resource requirements and also how your job is going to use them. So when you want to use multiple CPUs using OpenMP or another multiprocessing library like multiprocessing in Python, you're simply giving the job more CPUs per task, denoted by the N here. And it's also good to note here that giving a job the maximum number of CPUs, so 32 in most cases, isn't going to give you the most speed up, which again is why it's important to understand your software and its requirements. And then if you want to change the tasks per node, this is similar to changing the CPUs per task in that you can parallelize a job across a single node. The difference here is that these tasks can communicate using MPI, so you don't need OpenMP or another multiprocessing library. Then again, with MPI, you can use multiple nodes to do parallel work. So this is now splitting work between nodes as opposed to within a node. You wouldn't want to do this instead of using multiple CPUs or tasks within a node, though, because generally communication between nodes is slower than communication within a node. And also more nodes equals a larger job, which is going to affect your job's wait time. So finally, putting it all together, for the most optimized processing possible, you'd want to use a combination of multiple tasks per node and multiple nodes. And this kind of configuration would benefit like really large jobs that also have a good capacity for parallel processing. So this is going back to how your software needs to be properly configured to utilize the hardware if you want to really maximize parallel processing. So here's just a simple example of an SBatch script that you would use to run parallel jobs. Note the MPI wrapper goes before the singularity command, and the rest is as you'd expect in a normal batch script. You can also use srun instead of MPI run here. They both do the same thing when we're using Slurm. So in summary, what you're trying to do with parallel processing is improve the processing time of your jobs. So fortunately, some applications have already been built to utilize parallel processing. But if you're developing your own parallel applications, it's really important to understand your software well, because making it work in parallel can be quite labor intensive. So yeah, thanks. That's it for my presentation. I'm going to do a quick demo, and then I'm going to hand over to Jordan. Sorry. Can everyone see my terminal?
We can, Robin, but you might want to just zoom in a bit.
Cool. Okay, so here I've got a few SBatch scripts. I'm not going to run them all, but I will show you the basic structure. So this is one CPU, one node. So here you can see I've specified. So this is purely serial job. And I'm submitting this simple MPI scripture. Don't worry too much about the module and the source. This was just the configuration I used to get MPI versions to agree, because it can be a bit temperamental. And this is the Python script. Also, don't worry too much about this. World size is essentially the number of tasks I'm creating, and rank is the number of the task that I create when I use MPI. So this is simply using MPI through the MPI for Pi Python library. So if I submit this, submitted, it should run pretty quickly. Just check. It's actually probably finished already. Yeah, it's finished already. So if I check the logs for the output, so I told the SBatch script to write to this folder. So you can see here I've submitted the job, and world size is 1. The rank start at 0, so as you would typically count from 0 to whatever. And yeah, the world size is 1 because I submitted a job with 1 task per node. And now quickly, if I just submit a slightly larger job, so now this job is 4 tasks per node, it should also run pretty quickly. Yeah, it's done already. So that would be this one. So here I've submitted the job which uses 4 tasks per node, and you can see here that the world size is 4 because MPI is creating 4 different tasks, and then these are the different ranks. And you can see that they're not going to be in order because they've run simultaneously and at different times. So this order will kind of be random. The point here is just demonstrating how MPI is going to create you can use MPI to create a different number of tasks on a single node. So yeah, thanks for watching. I'm going to hand over to Jordan for the resource allocation and some more in-depth demo.
My full screen slides and grand window there. If you don't, just let me know. So thanks, Robin. As Robin mentioned, I'm going to talk about the resource allocation. Just as a brief extension on parallelism, I want to demonstrate the IDIA Meerkat pipeline as a framework for how to write a package to do parallel processing and basically make dynamic use of resources on the cluster. So it's not really to show you anything astronomical, even though it is a package for radio astronomy processing. It's rather to demonstrate to you how you could possibly come up with your own framework that does similar things across the cluster. So it's for HPC, high performance computing processing. You basically push a button and it submits everything to the queue, makes dynamic use of resources, and at the other end, you get your calibrated data. It separates every script that you run into its own Slurm job, which either does or doesn't use MPI, as Robin talked about, message passing interface. And optionally, you can actually use a different container for each step. You can actually insert your own scripts anywhere into the pipeline, and it supports different MPI wrappers and different containers for those. So I just want to briefly demonstrate this with a directory that I've prepared here. So this is basically the call for the software. So you pass in the data set, which is this particular raw data set, and then a container. In this case, I'm not using the default. And you call the build step. So basically that goes and reads the data and sets up your pipeline run according to that, such as how to divide up the work across MPI. So it's created this default config file. There's a lot of stuff in here, but I mainly just want to show you these Slurm parameters. So it's decided a good set of parameters is to run 16 tasks per node across 2 nodes. And in this case, chosen the maximum memory, which we will decrease. It's going to run on the main partition, which I'll explain a bit later. It's not going to exclude any nodes, but it optionally can if there's problematic ones identified. Uses this container, MPI run, as the MPI wrapper, which is loaded via a module. Uses the default account, which we also ought to change. And then it runs basically these scripts. And for each of them, there's a Boolean associated with it. This means whether or not that step can use MPI. So when it's false, the pipeline identifies that this should run a single CPU. And then this empty string basically means use the default container, but for each step you could specify a different container. And so I'm just going to edit this. I'll first of all not divide into frequency. It's just some further parallelism that you can do there. And then I'll change the default memory to say 50 gigabytes. And I'll change the time to perhaps an hour. And so I could then go and do what's called the run step here. And it essentially creates this submit pipeline script, as well as various SBatch scripts. So one example is the first step, partition. So this uses the parameters that I gave it for the MPI task, but it also can do an OpenMP type parallelism. So because of that, it chooses to use the entire memory because it's already allocated all the CPUs. So any remaining memory isn't usable by any task. So we may as well allocate all of it. It loads that module that I mentioned, and then the syntax is the MPI wrapper, singularity exec, the container, Python, the path to the script, and then any options that you pass into the script. As opposed to something like this SBatch file, which was identified as a non-MPI task. So this would just use a single CPU in the default memory, which is obviously much more appropriate here. So I can then go and run this submit pipeline script, which essentially submits SBatch jobs with dependencies on the previous one. So it captures the ID, and then for the next job submits with after OK, and then the syntax for the IDs delimited by a colon rather than a comma, basically. And you can kill on invalid dependencies. So this basically means cancel your entire pipeline run if one of them crashes. So this will instantly submit everything to the queue. So I can go and do that. It gives me some output. I can interact with those job IDs through something like the summary script. So this shows you it's now running, and you can see the entire pipeline has now been submitted to the queue. So I no longer need to interact with the data until it's done. And I could do all sorts of things, like I can, if there were any errors, it would show them here. The logs don't exist yet, but you would display errors. And so once you have the job IDs, then you can do a lot of things to interact with your pipeline run. And then I could also Just go ahead and kill those jobs. So that basically this extracts the job IDs and calls scancel. So that's what I wanted to demo for the pipeline. Make sure I showed everything I wanted to. Yep, so I now want to go into the resource allocation guide. And just to introduce this, ilifu is a shared resource limited cluster. We support a diverse range of projects between astronomy and bioinformatics. These all have varying resource requirements. And so because it's resource limited and shared, it's essential to make efficient use of resources. And that is essentially what we lay out in the allocation guide. In addition to that, not explicitly covered, but mentioned elsewhere, it's really important that you shut down your Jupyter server after you use it, which you can read about in our documentation or the previous training. This means that you're no longer allocated those resources, and so other users can come along and make use of it. And then generally, we suggest making use of sbatch with non-default parameters, so you explicitly specify, say, your memory CPU. And that ensures that we're making efficient use of resources. So when you're considering running your workflow, what's important is to consider which service to select. And there's different purposes for our different services and partitions. And you need to think about which one's the most appropriate for your workflow, which may actually depend on the maturity of your workflow, if you're still debugging versus if it's computationally stable. And so here you can see, as Hope presented in our previous training, the different services and partitions we offer, which I'm now going to go into in detail. So the login node is where you land when logging into the Slurm cluster. And it's for running basic bash commands like changing directory, making directory, listing its contents, and so on. But it's also for running Slurm commands such as srun, sbatch, scancel, sq, saccount, all of that. And this isn't running computational processes, but it's rather interacting with your jobs that are run on compute nodes. We also have Jupyter, which is a development space for writing, testing, and debugging your workflows. So new code and software workflows or routines. It's highly interactive within a Jupyter notebook environment. So you can do the tab completion. You can view doc strings, that is the help for different functions and modules. And you can also run different subroutines within the different cells. So it's highly interactive and generally for development, but it may also be a primary interface for stable workflows that don't need Slurm or shouldn't be submitted to Slurm for some reason, such as a short analysis routine or some other highly interactive workflow. We also have the devel partition, and this is for development of routines within a shared resource environment. So that means because you're sharing resources, you can quickly or instantly submit your jobs, but you're not solely allocated those resources. So you are in a kind of shared risk environment. It allows for interactivity via a shell, and is generally for testing higher level workflows and pipelines compared to Jupyter. And what you can do is interactively have an interactive session on the devel partition with the sinteractive command, which you can read about from the link there. And then we have the main partition, which is the default Slurm partition. And this is generally for stable, computationally heavy workflows and pipelines. So for instance, many small jobs allocated few resources, or a few large jobs allocated many resources, say MPI jobs across multiple nodes. And generally, we would suggest that these workflows have first been tested on one of the previous services, such as the devel partition, where appropriate, so that you're not trying to run a workflow that's not stable or is still being debugged and make use of the main partition where stable jobs should generally be run. We then have the high mem partition, which is for single high memory jobs that you can't split into multiple jobs using MPI. So if you can use MPI, that means you can split up the memory across multiple nodes. And so you should rather do that. But if you can't use MPI, and you have high memory requirements, then that's where you'd use the high mem partition. And then there's the GPU partition for jobs making use of GPUs, which isn't for jobs that only require CPUs. We have found some users, when the queue's full, would make use of the GPU partition because it's available, but rather you should use the devel partition in such cases where you can quickly or instantly submit your job. And then lastly, we have the transfer node, which I talked about in the previous training in more detail. But this is for internal and external copying for smaller or less frequent transfers not requiring Globus. And then you may also run basic bash commands that are inappropriate for the Slurm login node, such as wget to pull some data or a large removal of some data. But you can actually also run these on Slurm compute nodes, such as a single CPU, 1 GB RAM instance. So that brings me to how to allocate resources. And when doing so, you need to consider the 3 primary resources, which is CPU, memory, and wall time. Just a quick aside, the majority of our nodes on ilifu have 2 CPUs or sockets, each with 16 cores, but Slurm generally calls these all CPUs, not cores. And so we adopt this language in our documentation and presentations here. And then the wall time or elapsed time is the total runtime of a job according to a clock on the wall. And they use this language of wall time in that way to differ from CPU time, which is measured in CPU hours. And when running a parallel workflow with more than 1 CPU, this number would be different to the wall time. So the way to allocate resources is to accurately determine your requirements and then to use what you require. The effect of that is that you avoid wasting resources that are allocated but not used. You can increase resource availability overall on the cluster, and you can allow other jobs to run, including your own or other users' jobs. It improves the efficiency of our Slurm scheduler, which basically schedules all of the jobs according to their requirements and the availability of resources. And so if you accurately determine your resources, it's much more efficient. And it also increases your fair share priority. And in short, you can read the documentation about this, but in short, every project on Slurm has its own account against which your resource usage is charged. And so this affects your priority in the queue. And if you accurately specify your resources and don't over allocate, then your fair share priority, that is your priority in the queue, will be increased in general. And so it affects that, and it can potentially decrease your job wait time. If you more accurately allocate rather than over allocate, then in general, your job wait time will decrease. And so in order to determine your resource requirements, you need to know the parallelism of your software. And you also need to look at the way that it uses resources. So you can either do that by profiling previous similar jobs if you've already been running your workflows, or you can start testing your jobs by some scaling up tests, which I'll talk about both of these. So in terms of determining the parallelism of your software, Robin just talked about this, but just to reiterate a few points, it's important to know whether you can do CPU level parallelism limited to one node and generally implemented with OpenMP, or whether your program can do task level parallelism implemented with MPI and possible to run over multiple nodes. But it's important to remember many packages just use one CPU. And so if you were to allocate more than one, it's not actually able to make use of that. Beyond that, it's important to remember that many packages, even if they do parallel processing, don't scale linearly. And an example of that is shown on the right, just a mock-up example of how the wall time would decrease as a function of the number of CPUs or tasks. And so often the maximum performance is the least efficient. So that is the shortest wall time requires a very large allocation, and so it's very inefficient because it doesn't give you that much of an improvement. So you need to find some kind of middle ground, and this is where you need to test and see how it scales. Beyond that, even MPI jobs may actually get worse performance for increased allocation because there's a scatter-gather overhead associated with partitioning your data and this kind of internode communication that Robin talked about, and the IO involved in that, and potential reading and writing. And so, yeah, this is worth considering when you when you allocate your resources. And so what you want to do is consider the most efficient, which is often to break up into many smaller independent jobs, which would be a high throughput approach. Let me just try to minimize the background noise here, sorry. There we go, hopefully that's a bit better now. Okay. So in terms of profiling previous similar jobs, you first need your job ID. This is output when you submit your job, but if you've lost this, you can actually search for this with historical jobs. So say you wanted to search for a job named My Job, and you know a particular time range in which that was submitted, you could run this saccount command that I've displayed here. It will show you one line for each of those jobs. Or if you don't remember the name, you can omit the job name, or you can even omit the end time to just search for everything since that start time. Or if you're searching for very old jobs on old Slurm databases before we've done our cluster upgrades, you will also need to provide the cluster argument, either ilifu Slurm 20 or for the older database ilifu Slurm. So once you have your job ID, you can then search for specific information about your resource usage. And one example would be the max RSS statistic, which displays the maximum memory usage of a job as sampled by Slurm every 20 seconds. And so, for instance, you can get that with the saccount command, and you could compare that to your requested memory. You can run this within Jupyter as well, and this could help determine your future resource selection from the dropdown. You can see an example of a job that I've run. Sorry about that, everyone. Thanks for letting me know. I'll just carry on if you can see now.
Yep.
Okay, so I was just saying on Jupyter, you can also run saccount to find the max RSS statistic on previous jobs, and this can help you determine future resource selection from the dropdown. And so here I've provided a screenshot of a job I ran, which used 213 or 214 gigabytes compared to 232. So that's an efficient use. And just a couple of quick notes, the GN means gigabytes per node. And if you see a C, that would be gigabytes per CPU. And so once you've determined your memory requirement, you would then schedule future jobs with maybe a 10 to 20% buffer to avoid out of memory errors. But you should also avoid excessive usage of memory. So it may be in Jupyter, for instance, that the minimum node from the dropdown is able to meet your requirement for future jobs of the same kind. Or if you're submitting an SBatch, you can specifically set that value in your SBatch script. And then similarly with CPU and memory, you can determine used versus allocated or requested with the SF, which is Slurm efficiency. And so an example here would be SF and then the job ID, and it shows you the % used versus allocated. For memory, that's using the max RSS statistic. So here I've provided two examples. One is quite efficient with memory at about 92% and CPU at about 72%, whereas the other is very inefficient. And so that would be a dramatic over allocation of resources that should be massively reduced. So you can also run this within Jupyter to determine the future resource allocation from the dropdown. And then lastly, your wall time. Accurate estimation of your wall time in particular, all of these in fact, but wall time helps the Slurm scheduler to increase its efficiency and may reduce your job wait time. So you can, for instance, show used versus requested with saccount again. And I'll demonstrate all of these in a moment. So once you have determined your wall time, you could schedule future jobs with about a 20 to 30% buffer, which avoids it timing out, but you should also avoid excessive wall time. And so here I've shown an example where I requested an hour but used 21 minutes. And so you would do this, but if you're noticing that you're at risk of your job timing out, you can contact ilifu support to see if it's possible to increase your time limit. But hopefully, if you do these kinds of tests, you can accurately specify it. And then secondly, as I mentioned, you can run these scaling tests. And this would be either if you don't know how your jobs scale, or if you haven't run your jobs before, this would be a brilliant starting point. So for instance, you could run a small test job, such as a small allocation on a small subset of your data, test the wall time, run it again with increased resources. And during this period, while you're running your scaling tests, it's reasonable to over allocate, even though it may be briefly inefficient until you get an idea of your requirements. This is a reasonable thing to do. Or if you happen to underestimate, but your test is small enough, it doesn't really matter if it crashes. If it's like a few minutes long or something, can you just repeat until you get an idea? And so as you repeat this, you can see how the resource usage scales as a function of the input, such as the input data volume. Or if you are doing parallel processing, you can see how it scales as a function of CPUs or tasks. And so by the end, you should have a good idea of how that scales and what an efficient choice would be, which again may not be the maximum performance. And then you could allow for a buffer for future jobs. And so as you're doing this, or as any of your jobs are running and you want to know the real-time statistics, you can, for instance, get the max RSS from SStat, which you can run with the syntax shown here. This gives kilobyte units, so you just divide by 1024 to the power of 2 for gigabytes. Or you can run something like top or htop to display a dashboard of real-time statistics on memory and CPU. So say you were on Slurm, you would then SSH to the compute node that you're running on, which you could display with either SQ or saccount. Or you could open the Jupyter terminal if you're running your job on Jupyter. In the first case on Slurm, you would first need a job running on that node, and you would need authentication forwarding, which is done with the option A, so SSH-A, and then your username at Slurm when you first log in. But once you've SSH'd onto the node or opened the Jupyter terminal, you could run htop option new user, and this shows you your real-time dashboard of the different running processes, such as the master process and the spawned ones, and you can monitor your real-time usage. In terms of the defaults and maximum, that's displayed in the table here, also available in our documentation. I won't go through it in detail, but essentially each of the different partitions and services have different defaults and maximums. So you need to consider that when you're allocating. And as I say, often you don't want to just use the default. It's important also to note that if you use all of the CPUs or all of the memory, that node becomes fully allocated. And so any remaining CPUs or memory are unavailable to other jobs, including your own jobs. So if you have a process that can use all of one but not the other, consider leaving headroom so that yours or other people's jobs can make use of a small amount of the remaining resources for smaller jobs. And then what's also important is setting your account. So as I mentioned, each project we support has a different Slurm account, and this is what we charge your resource usage against, which affects your fair share priority. And so you can view these accounts with the syntax listed here, which I'll demonstrate in a moment. And you can also view your default account, which is the one that's used when you don't specify account, which may be inappropriate. And you can also change your default if you think that it should be a different account. And then importantly, when submitting something like an SBatch job, you can set the account with the account parameter and then the name of your account. So let me now demo some of those things. So I'll just pull up my terminal again here and see that I disconnected. So just pull up the test here. So you can see, for instance, if I run the S account, this account call that I provided in the slides, you can see this shows the elapsed versus time limit. So this isn't terribly efficient, but it's not horrible either, this particular example. You can see also the max RSS example that I showed. This isn't the one that I expected. And this is it. So you can see the used versus requested. And then you can also see an example of SF that I showed as well. So you can see as a percentage memory utilized and the CPU utilized. And then what I also want to show is HDOP. So I don't have a job running right now, but say I did on compute 001. It's a bit slow for some reason. So I could run HDOP option U user, and I don't have anything running here. And in fact, I could only SSH because I'm an admin. So you would first need to have a job running. And so you would see the memory and CPU percentage utilized for the different jobs, the master and spawned. You can do similar with top, but this is basically without showing the spawned processes. So this is really useful as a real-time dashboard. You could connect through a different window, or you can run this in the Jupyter terminal, as I mentioned. And then lastly, I want to show you some of the accounting commands. I'm just rather going to copy and paste them since they're a bit long, but basically you could run this one to display all your accounting groups. So those are all mine. I'm part of quite a number of projects. And then you can also show your defaults. And in my case, it's the pipelines group that I can see listed in full here. And then, yeah, as I mentioned, you can change the default here. I'm not going to do that, but you can do so. And then what's important is actually setting your account when you run your job. Okay. I also now want to move on to the Soreo archive. And this is just a brief slide and demo before we finish and take questions. So we have documented this in terms of how to get set up, but also how to configure a transfer, which I'll show you in a moment as well. But basically, this is what the interface looks like. And you can push to IDIA from here, which makes use of a grid FTP or Globus transfer that's very efficient and places your data in your raw data directory. But first, you'd actually need to register on the archive and have the PI of a particular project you want to push, request access. I need to actually update this here. It's rather a link that you can find in our documentation. But you can also get in contact with us. And in particular, if you don't have a project on the ilifu for that Meerkats project, then you would need to request one, and there's certain eligibility criteria. And if it's an open time project, for instance, there would be a form that you fill out for this. So I'm going to go to the archive interface now and show you some things. So this is what it looks like. It shows you data for which you have access. But what I wanted to show in particular is how to configure an MVF to MS push. And so this basically relates to how to select or average data as you push it. There's these buttons up the top. So if you're clicking 4K, everything you set corresponds to only data sets that have the 4K label. So that's there. Okay, this is going weird. I'm just going to reload that. About this. You guys still hear me okay, right? So you can see these 32 kWs, and that's 32K wide. So that's all of these ones displayed here. And that means if I click the 32K button, this config I'm setting up would only apply to those as I push it. So for instance, you may not want the ingest RFI category. You can read about those from this link here. You can also read about all the parameters with this link here. But you may not want the ingest RFI flag. This is kind of what we would recommend as the default, just CAM and data loss flags. If you don't need to do polarimetry, you probably don't need all your polarization, so you could set this to false. You can also set this down here as the polarization selection as HHVV, that's like XXYY. So this halves your data volume and just means that you're not interested in the polarized emission. You can also similarly select your channels. So for instance, I'm just really quickly going to flash up the documentation here so you can find our MVF to MS config. And here you can see the recommended value if you don't need anything above 1420. If you're doing spectral line science, then you could set your channel selection as that. If you have 32K data, but you only want 4K, you could bin by a factor of 8, and that would give you 4K data that's 8 times smaller. And you could, even if you want to discard the first dump, you can read about that in the cookbook, which I opened earlier. So that's all this stuff. Shows you the parameters, and then you can also read about the flags here. But these are what you need to consider when you push data. You can push calibrated data. Although you can, if you're using this, you can also download the final images as produced by this same pipeline that gives you this calibrated data. So you're probably rather interested in uncalibrated, and perhaps, you know, for instance, you want just 4K all polarization, and you would do something like this. And then you would go back here and you would push to IDIA. So you would push this button, and this will only show up if you have been configured to be able to push for this project. And so if you're not, you'd need to get in contact with us, and we can, if it's a project for which you're set up on ilifu, then we would set that up for you. What we want to avoid is pressing this direct download link. So if you are pushing to IDIA, please don't use this, please rather push. If you want to copy to elsewhere, this is probably the way to do it. But if it's to IDIA, you should use this push, which is much more efficient on both sides, and it's also more efficient for you. So that's most of what I wanted to show for the Soreo archive. So that's everything from me. Thanks for listening, and we've got some brief time for questions now.
Gerrit has asked, in terms of the archive, is that only available for astronomy type data? What is the setup on the back end, front end, and also what's the type of storage and current size? Jordan, do you want to take that question? I feel like you have a pretty good understanding of the archive.
Yeah, so yeah, it is just for astronomy data, but I guess it's more like a interface that uses the common backend that you could do for any project. So yeah, in terms of backend, I mean, it uses a Globus, which uses grid FTP. And I guess it also has like a dedicated link between us at IDIA and the Soreo archive at CHPC. And so there's that infrastructure that improves the service. But then generally, if you've got anything similar to that and you're using Globus, you can get the same quality of transfers, which are presented in the previous training. But basically, we're talking like gigabits per second for those kinds of configurations.
Just to further on that, Gerrit, so that the archive itself is not hosted by IDIA, it's hosted by the Soreo Observatory as a service, and I believe it's on Ceph storage, Jordan, as like immediate storage, but then has tape as archival backup, so they can pull from tape onto Ceph storage and then stage it to be made available for download. So yeah, that's the kind of astronomy archive for the Meerkat telescope.
Okay, thanks, Jeremy. Thanks, Jordan. Yeah, I'm just interested in some kind of archive for bioinformatics as well. So,
of course, good to know what's out there.
yeah.